Welcome back to Physics 192. I'm Gerard Blanchard. Last time, we introduced the concept of electric charges being the source of electric fields, and we gave you the equation that the electric field created by a charge is equal to a constant K times the charge of the charge creating the electric field divided by the distance that you are away from the center of the charge squared, and in the direction away from the charge. This time, we're going to apply that to some questions. 3-point charges are placed on the x-axis. A charge of 3 microcoulombs, that's 3 times 10 to the minus 6 coulombs, is at the origin. A charge of -5 microcoulombs is at 20 centimeters, and a charge of 8 microcoulombs is at 35 centimeters. What is the force on the charge at the origin? So, draw your diagram, and remember that the force on the charge at the origin is going to depend on the electric field created by the other two charges, not its own field, because a charge cannot feel its own electric field. It can't exert a force on itself, but the other two charges will create the electric field that is exerting the force on the charge at the origin. So once again, draw your diagram, list everything you know, figure out the electric field being created at the origin, and then the force on the charge at the origin. Go ahead and give that a try. Okay, let's draw a diagram of that. First I'll draw my x-axis, and I'll draw my 3 charges. Here's my positive charge. We'll call it Q1, and it has a charge of 3 microcoulombs, which is 3 times 10 to the minus 6 coulombs. And that is located at x1 is equal to 0. Here is my second charge, and it's a negative charge. Q2 is equal to negative 5 times 10 to the minus 6 coulombs. And it is located at x2 is equal to 20 centimeters, or 0.2 meters. And my third charge is a positive charge, and that is Q3 is equal to 8 microcoulombs, or 8 times 10 to the minus 6 coulombs. And it's located at x3 is equal to 35 centimeters, or 0.35 meters. Okay, now, we are asked what is the force on the charge at the origin, or what is the force on Q1. So we're asked what is the force on charge 1. Well, it is the electric force. So force 1 is equal to charge 1 times the electric field at its location. Well, we know what charge 1 is, but we're going to have to figure out what the electric field is. What creates the electric field that the charge feels? Well, the other charges do. This charge creates an electric field at this position, and this charge creates an electric field at this position. So the electric field is equal to the electric field created by charge 2 plus the electric field created by charge 3. Now what is that? The electric field created by charge 2 would be our constant K times Q2 divided by the separation between charge 2 and charge 1 squared. So I'll call that R12 squared. And it's in the direction away from Q2. At least that's our equation. That's our equation for calculating the electric field. Let's put some numbers in there. The electric field from charge 2 is K, which is 8.99 times 10 to the 9 times Q2, which is a negative 5 times 10 to the minus 6, divided by the separation between charge 2 and charge 1 squared, which would be 0.2 squared away from Q2. And so E2 is equal to, let's calculate that out, 8.99 times 10 to the 9 times a negative 5 times 10 to the negative 6 divided by 0.2 squared, and that gives me 1.12 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6, sorry, negative 1.12 times 10 to the minus 6 away from Q2. And so what is negative away? Well, negative away is actually towards. So the electric field from charge 2 is equal to 1.12 times 10 to the 6 toward Q2. So at this position, at the origin, Q2 is creating an electric field that is towards Q2. So if I go from here towards Q2, I see that the electric field E2 is 1.12 times 10 to the 6 towards, and that would be 1.12 times 10 to the 6 newtons per coulomb, towards Q2, or in the positive x direction. So at this position, this charge is creating an electric field that points in the positive x direction, or points towards the charge. Just as we said before, the electric field points towards a negative charge. And so there we have E2. How about the electric field from charge 3? A little separator here. E3 is very similar. K Q3 over R13 squared. Sorry, not towards, away from, that says away, A-W-A-Y, away from Q3. So E3 would be 8.99 times 10 to the 9 times Q3, which is 8 times 10 to the minus 6 over the separation between charge 3 and the origin, which is 0.35 squared away from Q3, or E3 would be equal to 8.99 times 10 to the 9 times 8 times 10 to the minus 6 divided by 0.35 squared gives us 5.87 times 10 to the 5 newtons per coulomb away from Q3. So the electric field from Q3 is away from Q3. So at this point, this charge is creating an electric field away from Q3. So if we're here and we want to get away from Q3, we'd have to move in the negative x direction. So E3 is 5.87 times 10 to the 5 newtons per coulomb away from charge 3, or in the negative x direction. So now we have the two component electric fields created by the two charges. So, and they're both in the x direction. So E x would be equal to E2x plus E3x. So the component of the electric field in the x direction would be positive 1.12 times 10 to the 6 newtons per coulomb from Q2, and negative 5.87 times 10 to the 5 newtons per coulomb from Q3. So that would be 1.12 times 10 to the 6, that's from E2, and then minus 5.87 times 10 to the 5, and that's from E3, or EX total is 1.12 times 10 to the 6 minus 5.87 times 10 to the 5, which would give me 5.33 times 10 to the 5 newtons per coulomb. So the total electric field, when we add up the contributions from charge 2 and charge 3, are 5.33 times 10 to the 5 newtons per coulomb in the positive x direction. And of course, since there's no electric field in the y direction, EY would be 0. So we have an electric field in the positive x direction and not at all in the y direction. Okay, so now that we know the electric field, we can say that the force on charge 1 in the x direction is equal to charge 1, which is, well, it would be Q1EX. So force 1 in the x direction would be 3 times 10 to the minus 6 coulombs times 5.33 times 10 to the 5 newtons per coulomb in the positive x direction. So the force on charge 1 in the x direction would be 3 times 10 to the minus 6 times 5.33 times 10 to the 5, or 1.56 newtons in the positive x direction. The force in the y direction would be Q1 times the electric field in the y direction. So it would be Q1 times 0, since there's no electric field in the y direction. So the electric force on charge 1 in the y direction is 0. So what is the electric force on charge 1? It is 1.56 newtons in the positive x direction and 0 in the y direction. And that is the question that we were asked to answer. Let's work another question. Here's a question where we're going to have to consider both the x and the y components of the electric field. 3 point charges are fixed in place in a right triangle. What is the electric force on the 1 microcoulomb charge due to the other 2 charges? And you have a diagram showing you where all of the charges are. So draw your own diagram and start thinking about how you are going to answer this question. Okay, let's draw our diagram. Draw my x-axis and my y-axis. Okay, and I have one charge. We'll call that Q1 is equal to negative 0.6 times 10 to the minus 6 coulombs. It's 0.6 microcoulombs. I have a second charge. I'll call that Q2, 0.8 microcoulombs, or 0.8 times 10 to the minus 6 coulombs. And a third charge, which I'll call Q3, and that is equal to 1 microcoulomb, or 1 times 10 to the minus 6 coulombs. And we were told that this distance right here is 8 centimeters, or 0.08 meters. And this distance right here, we were told, is 10 centimeters, or 0.1 meters. Okay, well, let's go ahead and figure out this distance here, because we will ultimately need to know that. And so if we call that distance x, then we know that x squared plus 0.08 squared is equal to the hypotenuse, 0.1 squared. Or x squared is equal to 0.1 squared minus 0.08 squared, or x is equal to the square root of 0.1 squared minus 0.08 squared. So what is this length right here? The square root of 0.1 squared minus 0.08 squared, and that is 0.06. So we know that this distance right here is 0.06 meters, or 6 centimeters. And we were asked for the force on charge 3. So the force on charge 3, let's write that as a 3, force on charge 3 is equal to charge 3 times the electric field at its position. And I'm going to break that up into x and y parts. The x component of the force on charge 3 is equal to charge 3 times the electric field in the x direction. And similarly, I'll go ahead and write it down a little bit further down on the page. The y component of the force on charge 3 is equal to charge 3 times the y component of the electric field at the location of charge 3. Okay, so once again, we want to know the force on this charge. Well, it's going to be equal to the charge times the electric field. We have to figure out the electric field, and the electric field is created by this charge and this charge. Okay, so we'll write that as E vector at this position is the electric field from charge 1 plus the electric field from charge 2. And so the EX would be equal to E1X plus E2X, and EY would be equal to E1Y plus E2Y. So we have to figure out the X and Y components of both of the electric fields from charge 1 and charge 2. Okay, let's go ahead and do that. Once again, I'm going to start a little bit further down the page to give me room to come back up here. And I will say, I'll start here. E2, E1, let's do E1. The electric field from charge 1 is going to be equal to K times Q1 over the separation between charge 1 and charge 3, R13 squared, away from charge 1. So the electric field created by charge 1 at the location of Q3 is equal to 8.99 times 10 to the 9 times Q1, which is negative 0.6 times 10 to the minus 6 coulombs over the separation between charge 1 and charge 3, which is 0.06 squared, away from Q1. And let's figure out what that is. Okay. That is 8.99 times 10 to the 9 times negative 0.6 times 10 to the negative 6 divided by 0.06 squared. And that gives us a negative 1.50 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 newtons per coulomb away from Q1. And so negative 1.5 times 10 to the 6 away from Q1, and negative away gives us E vector 1 is 1.5 times 10, 1.50 times 10 to the 6 toward Q1. Okay, so the electric field that charge 1 creates at the location of charge 3 is towards Q1. So if I'm at the location of charge 3 and I go towards Q1, that would be in this direction. So E1 is 1.50 times 10 to the 6, or 1.50 times 10 to the 6 newtons per coulomb towards Q1, or in the negative x direction. Okay, we have to do the same thing for the electric field that charge 2 creates at the position of charge 3. So E2, we'll call that E2, would be K Q2 over R23 squared away from Q2, or E2 is equal to K, which is 8.99 times 10 to the 9 times Q2, which is 0.8 times 10 to the minus 6, divided by the separation of Q2 and Q3, which is 0.1 meters. So that would be 0.1 squared away from Q3, or, and these are vectors, E2 is 8.99 times 10 to the 9 times 0.8 times 10 to the negative 6 divided by 0.1 squared, and that would be 7.19 times 10 to the 1, 2, 3, 4, 5 10 to the 5 newtons per coulomb away from Q3. So the electric field created by charge 2 is 7.19 times 10 to the 5 newtons per coulomb away from Q3. So let's go back up to our diagram and let's look at that. So the electric field created at this point by this charge points away from this charge. So I have to draw it, if I follow this line, I draw it like this, and it is 7.19. So E3 is equal to 7.19 times 10 to the 5 newtons per coulomb in this direction, which is both in the x and y direction. So we're going to have to break that up into x and y components. So we're going to have E3x and E3y. So we're going to have both an x and a y component. Actually, okay. And so to break this up into components, we're going to need an angle. And let's use this angle right here. and we'll call that theta. So if this is our angle right here, then the x component is actually going to be E3 adjacent and E3 opposite. So this is the adjacent side, adjacent to the angle, and this is the opposite side, opposite the angle. Now what is this angle? Well, this angle right here is going to be the same as this angle in here, same as this angle in here. And we can figure out this angle using our trigonometric functions. The sine of theta, the sine of this angle right here, is going to be the opposite side divided by the hypotenuse. So sine of theta is going to be 0.08 divided by the hypotenuse, 0.1. So theta is equal to the inverse sine of 0.08 divided by 0.1, or theta is equal to the inverse sine of 0.08 divided by 0.1, and that gives me 53 degrees. Okay. So now we know everything we need to know to figure out the total electric field at this point, both the x and the y components. So now we're at the stage of figuring this out right here. And so Ex is going to be the x component from charge 1. So this side right here, or this vector right here, it's completely in the negative x direction. So the x component of the electric field from charge 1 would be negative 1.5 times 10 to the 6, since it's completely in the negative x direction. And the electric field from charge 2 in the x direction is going to be this side of our electric field triangle. So that would be plus 7.19 times 10 to the 5 times the cosine of theta. So times cosine of 53 degrees. That is our adjacent side. That is this part of, that is the x component of this electric field right here. So the electric field in the x direction is negative 1.5 times 10 to the 6 plus 7.19 times 10 to the 5 times cosine of 53 degrees. And that gives me a total negative 1.07 times 10 to the 6 newtons per coulomb. So the total electric field is in the total x component of the electric field is in the negative x direction. Now we just need to figure out y. Ey is equal to E1y. It's equal to the contribution to the electric field from charge 1 that's in the y direction. And that's going to be 0 because this is the electric field from charge 1 and it is not pointing in the y direction at all. It's only pointing in the negative x direction. So that'd be 0 plus the y component of this electric field. So that is going to be negative E2 opposite, so it would be negative 7.19 times 10 to the 5 times, since this is the opposite side, that's going to be sine times the sine of 53 degrees. And so EY is going to be negative 7.19 times 10 to the 5. It would be negative 7.19 times 10 to the 5 times the sine of 53 degrees. And that would be negative 5.74 times 10 to the 5 times 10 to the 5 newtons per coulomb. So the total electric field from charge 1 and charge 2 at the location of charge 1 is in the negative y direction, and it would be negative 5.74 times 10 to the 5 newtons per coulomb. So now we're finally in a position to answer what is the force in the x and y direction on charge 3. So now we're back to here. The x component of the force on charge 3 is Q3, which is 1 times 10 to the minus 6 coulombs, times EX times negative 1.07 times 10 to the 6 newtons per coulomb, or the x component of the force on charge 3 is 1 times 10 to the minus 6 times negative 1.07 times 10 to the 6. That gives me a negative 1.07 newtons. So the net force on charge 3 is in the negative x direction, a negative 1.07 newtons. And the y component, Fy3, is 1 times 10 to the negative 6, that's Q3, times the y component of the electric field, which is negative 5.74 times 10 to the 5. Got that from right here. And that tells me that the y component of the force on charge 3 is 1 times 10 to the negative 6 times negative 5.74 times 10 to the 5. That is a negative 0.574 newtons in the y direction. So what is the force? What is the force on charge 3? It is negative 1.07 newtons in the x direction and negative 0.574 newtons in the y direction. And that answers the question that we were asked. So we have been working with the electric field created by a point charge. The electric field of a point charge depends on a constant K. It depends on the amount of charge that's creating the electric field. It points away from a positive charge and towards a negative charge. And the electric field strength decreases as the square of the distance that we are from the center of that charge. Now we've encountered this before. We've encountered this with gravity at the end of Physics 191. When we are close enough to the surface of the Earth that the Earth looks flat, then we have a constant gravitational field. but when we are far enough away from the surface of the Earth that the Earth begins to look like a sphere, then the gravitational field also decreases as the square of the distance from the center of the Earth. So for a large flat Earth, the gravitational field is constant. For a spherical Earth, the gravitational field decreases as 1 over r squared. So, and similarly, for a spherical charge, the electric field decreases as 1 over r squared. But what if we had a large flat charge? In that case, we get a constant electric field. Let's look at the equation for that. The electric field of a flat charged plate is 2 pi times k, our same constant k, times the charge on the plate, q, divided by the area of the plate, A, and it points in the direction away from Q. So for a flat charged plate, we have a constant electric field, just as for a flat Earth, we have a constant gravitational field. So once again, for a flat charged plate, the electric field is 2 pi times our constant k times the total charge q on the plate divided by the area of the plate. Now, often what we encounter are two plates close together that have opposite charge, one with a plus q and one with a minus q, and let's say that they have the same charge. And here's a diagram of that situation. In that case, we have 2 pi kq over A from the positive plate and 2 pi kq from the negative plate. Or in other words, the total electric field in between the plates is 4 pi times k times q divided by the area of a single plate. And the electric field points away from the positive plate, away from the positive charges, and towards the negative plate, or towards the negative charges. So, when we have the situation that we have two flat plates, they have equal and opposite charge, one has plus q and one has negative q, and they both have the same area, then the electric field between these two plates is 4 pi times our constant k times q, the charge on the positive plate, divided by the area of an individual plate. And this is a situation that we'll encounter in future situations. So please bear in mind that when you have large flat plates, you have a constant electric field, and we actually can now calculate the electric field in between those large flat plates. So, we've talked about electric fields created by charges and the forces that the electric fields exert on other charges. Next time, we're going to talk about energy. As it turns out, the electric force is a conservative force, so there is a potential energy function associated with the electric force, and we will learn how to work with that electric potential energy next time. Until then, think physics.